Hi everyone, welcome back. Today we're starting something really exciting, our last unit, which focuses on machine learning operations, or MLOps, as it's commonly known in the industry. So what exactly do we mean by MLOps? MLOps is the standardization and streamlining of our machine learning lifecycle management. As we move through our machine learning lifecycle, there are different key areas that we can automate, integrate, and deploy using some of the cloud-native and CI/CD principles that we've already built. Let's talk a little bit more in depth about the machine learning lifecycle and what it is exactly. Machine learning always starts with a research question. That research question is going to be, what do we actually need to do? What are we trying to predict? And what do we need to classify? The first stage after defining our research question is our data collection and pre-processing. Our data collection could be collecting signal traces from our observability platform, external data sets, telemetry from IoT devices, or whatever that might be. Data collection and pre-processing is a step where you actually amass data into some central location and then do any relevant cleaning or transformations on it that you might need to do. Next up is our experimentation and evaluation stage. That's where we actually build our model. We do our training and our testing, and then we evaluate those initial metrics. This could also be where your hyperparameter tuning happens. In large language models, this is where we would be conducting fine-tuning. After we've tuned our model, the next step is model deployment, where you take your model and then you pop it into a production system. You need to persist your model in a location where it can be accessed by systems that need to use it. It's important to note that you will need to determine your model retraining schedule in this phase as well. Following deployment, we have serving and inferencing. In this step, there'll be some mechanism that can call your model and then generate new predictions or new classifications or do something useful with that model. Finally, we have monitoring and maintenance, where we make sure that we check out our model's performance. We make sure we can detect drift and that we can handle ongoing operational concerns. Let's examine the key roles and disciplines that accompany each stage as we move through the AI or ML lifecycle. Our research question stage is going to be driven by our domain experts. These are the people who really understand the problem, and they know what kind of task needs to be achieved with the model. Those are going to be business stakeholders or researchers. They work with the data scientists to define a research question. Data collection and pre-processing is going to be a combination of data engineers and data scientists. Those are two different disciplines. Data engineers are going to be more focused on building data pipelines and on using data engineering tools to define data transformations and ETL tasks. Data scientists work alongside them in this phase to help data engineers understand the requirements of the model. The experimentation and evaluation stage is driven by the data scientists. That's where we shine. We're going to build our models, conduct our experiments, keep track of the results, do hyperparameter tuning, and celebrate when we build something cool. Model deployment is generally done in collaboration with software engineers and SREs. Next, we have our model serving and inferencing. Depending on the type of data or the type of model we have, and whether we're conducting online inferencing or batch inferencing, there are going to be different tools and requirements to consider. We need to make sure we have our software engineers and SREs involved in our model serving and inferencing as well. Monitoring and maintenance should be a collaboration between observability teams and data science teams. Data scientists are going to be able to identify model drift, while observability teams are going to be able to help us build dashboards, collect metrics and traces about our system overall, and make sure that the end-to-end unknown questions can be answered. Now let's dig into the key tasks in each stage of our machine learning lifecycle, starting with defining research questions. In our first stage, we're going to define our research questions. Those again are going to come from domain experts, or they're going to be defined by business goals. Some examples of research questions might be, how can we prevent fraudulent actors from onboarding onto our platform or from using our product? In the medical domain, we might ask, how can we better identify cancerous cells from medical imaging scans? Research questions require domain experts because domain experts know what questions to ask. The quality of our questions defines the quality of our outcomes. If we build models and systems that address a problem that we don't really have, we'll have wasted a full cycle, or many cycles, on models that are functionally correct, but not actually helpful or useful. We want to make sure that we're bringing in domain experts in order to help define our research questions. Now let's move on to our data collection and pre-processing stage. This encompasses a couple of parts. First, we have data collection and storage. We're going to find our data sets, collect new data if we need to, build some ETL pipelines, and identify the appropriate databases and schemas that we want to use. Then we have exploratory data analysis. This is where we understand the dataset as fully as possible. After that, we have data cleaning. We're going to convert data types, impute missing values, and remove outliers if that's required. Then we'll have our feature engineering. That's where we transform our data to be usable or understandable by a machine learning model. This includes feature extraction and feature selection. Let's dive deeper into the data collection and storage components. We have different sources for data collection, including open source data repositories, internal data, and web scraping. For ETL, the tools that we want to use are things like pipelines, dbt, and Airflow. For data storage, we can use databases, whether they're self-managed or cloud-managed, data warehouses, and data lakes. These data stores can be either relational or non-relational depending on our data requirements. Now let's talk about exploratory data analysis in more detail. For exploratory data analysis, we want to make sure we capture the summary statistics, the number of observations, the number of classes, and the number of variables in our dataset. Those variables need to also be accompanied by clear definitions. What does this actually mean? What does this variable represent? How much of the data is populated? What's the cardinality? Can we trust the provenance of this data? Then we usually support that through visualizations. We use histograms, scatter plots, and dimensionality reduction, where we'll take high-dimensional data and reduce it into 2 dimensions, and then plot it. Moving on to data cleaning. We need to make sure that we are standardizing our data cleaning process. We often reuse our data cleaning functions when we are conducting inferencing. As new data is sent to our trained model, we need to make sure that our data is able to undergo the same transformations we used when training the model. For example, we might want to convert integers into floats, or we might want to do some timestamp normalization. Maybe instead of using the actual timestamp itself, we create a feature that represents hours since some event, or minutes since some event. If it's textual data, do we want to use case folding? Do we want to do any encoding? When we're imputing missing values, we can impute with a median or mean or previous value or none. For removing outliers, we need to make sure that we understand if our outliers are actually meaningful. Do we want to keep our outliers? Are there any implications for our inferencing stage if we remove outliers or if we keep them? Finally, let's discuss feature engineering. Feature engineering encompasses many different techniques. With categorical data, we might want to conduct one-hot encoding or label encoding. With textual data, we might want to create embeddings. For time series data, we might want to remove seasonality from that time series. Feature extraction is taking existing data and pulling out useful features from it. For example, we may have raw image data that we convert to numerical matrices. Another example of feature extraction is combining variables, creating time since X features. For feature selection, we want to make sure we're using statistical tests, like feature correlation and variance inflation factor, to make sure that our features are legitimate and will provide meaningful value to our model. Now let's discuss some key considerations for data collection and preprocessing for MLOps implementation. There are many options for data collection and ingestion. Data warehouses are a very common solution. Warehouses are going to have some level of standardized data outside of raw production databases. Warehouses are a centralized store for data that can come from many production databases. That data goes through some ETL processes and then lands in the warehouse. A data lake is also a large centralized store for data, but data lakes store raw, diverse data like structured, semi-structured, and unstructured data. NoSQL databases are becoming much more popular, especially vector databases, given the amount of text data that we work with for AI and ML applications. EDA doesn't necessarily have to be repeated after it's first performed, but it is a critical step before moving on to our cleaning and preprocessing. Exploratory data analysis is generally not part of your machine learning pipeline per se, unless your EDA is helping you do some downstream task. Generally, we'll eyeball the EDA and use it to inform our decisions and then move forward. Regarding data cleaning automation, once we've identified exactly how we need to clean our data, this step can be fully automated in most cases. For example, if we've identified that timestamp data in our warehouse needs to be converted into UTC or does not need to be time zone aware, we can write those data cleaning functions and then fully automate those steps when we run our model training service. Data preprocessing, including data cleaning, can be its own microservice in our MLOps pipeline. This is because data preprocessing can be used for both training and also for inference. We want to be able to reuse our preprocessing functions in multiple places, which makes a good case for having preprocessing exist as its own microservice. If the preprocessing step is going to involve any scaling of features or referring to some data structure like a label-encoded dictionary, then you need to make sure that those values are available at inference as well as at training. That's another artifact that you might need to persist alongside your model and your model weights. Next, we have experimentation and evaluation. In our experimentation and evaluation phase, we have a couple of key tasks. First, we select a model, then we build it using the required tools. Then we train, test, and evaluate, and finally tune the model's hyperparameters. Let's walk through each of these steps now. The first critical step in experimentation and evaluation is model selection, which involves key decision points that will fundamentally shape your entire machine learning approach. You need to determine what model family is appropriate for your data, whether you're dealing with supervised learning, unsupervised learning, semi-supervised approaches, or reinforcement learning scenarios. Second, clarify exactly what task you're trying to achieve. Are you building a classification system, a regression model, or do you need forecasting capabilities? Third, determine the appropriate model architecture for both your data characteristics and your specific task requirements, considering your deployment environment and whether you'll be using deep learning approaches, traditional machine learning, or generative AI solutions. Moving to the second step, build the model. Once you've selected your model approach, you need to make several technical implementation decisions. First, what libraries and frameworks will you use? PyTorch offers dynamic computational graphs. Scikit-learn provides traditional machine learning implementations, while TensorFlow and Keras give you production-ready deep learning capabilities. Second, how will your preprocessed data be input to the model? You need to define exact input and output dimensions and determine if additional processing needs to happen internally within the model itself. Finally, consider model creation specifics like optimization algorithms, loss functions, regularization techniques, and how your model's weights will be persisted. Now we reach the third step, train the model. First, containerize your model training code and plan for remote machine execution to ensure reproducibility and environment consistency. Second, carefully assess your hardware requirements beyond just GPU considerations, including memory, disk space, and bandwidth requirements. Third, determine how you'll persist and access the trained model, whether through local storage, cloud object storage, or specialized model registries. Fourth, implement checkpoints during training as your safety net against hardware failures and optimization tools for resuming training and implementing early stopping strategies. Next, test and evaluate the model. First, your evaluation criteria are directly determined by the task you set for model training, and these technical metrics must align with your business objectives. Second, plan how you'll access your evaluation criteria through automated testing pipelines, interactive dashboards, or manual review processes. Third, ensure your test data preprocessing exactly matches your training pipeline for consistency. Fourth, remember that quantitative metrics are only part of model evaluation. Case studies and real-world trials are equally important. Finally, evaluate feature importance to understand what your model actually learned and identify opportunities for system optimization. Our final step is hyperparameter tuning, the systematic optimization of variables that are external to your model but critically affect its performance. Hyperparameters are configuration settings you choose before training begins, including learning rate, optimizer choice, number of clusters for clustering algorithms, and cutoff thresholds for classification tasks. The tuning process requires systematically rerunning your entire pipeline while recording results for each hyperparameter combination. Two critical operational considerations emerge here. First, where and how are your experimental results recorded? Second, conduct proper statistical testing to determine if performance differences are actually significant, using t-tests and confidence intervals to make data-driven decisions. Now let's discuss some key considerations for model experimentation and evaluation that are essential for production MLOps. First, how and where will the model training be conducted? Is that training going to be distributed? Is it going to be localized on one machine? How often will it be retrained? Next, what automated pipelines can you use for your model training? Once you've pushed or merged a pull request into main, does that kick off a new job where the model is trained? Another important consideration is how will the model training service access the required data? Does that model training service need its own set of credentials so it can read from your warehouse? Is it going to train exclusively on data that's kept locally? Is it a CSV that gets output that's then local for that model to use for training? Finally, how are you going to know exactly what data was trained on and that it was pre-processed correctly? This is where things like data catalogs come into play. Data catalogs are ways of doing exactly that, cataloging the data that your model trained on. We can also do things like further attestation of the data that we trained on using hashing functions or hashing algorithms. Let's talk about some important distinctions between research and production considerations. For experimentation and evaluation, if you're conducting research, which is different than just implementing a machine learning model in production, there's another step in our stage 3, which is benchmarking the model against state-of-the-art models. Evaluation against those benchmarks is going to require some additional tests. For example, you might need to do some students' t-tests to determine p-values for how well your model performed compared to existing state-of-the-art and test for statistical significance. When we're exploring which features are the most important for our model, we might also want to add features or remove features, and the results of those experiments need to be recorded as well. So recording your experiments and all of the evaluation criteria is a job in and of itself. Next up, we have model deployment. Sometimes this is called model ops. In our model deployment, we're going to have a couple of key things. First, we're going to have our model artifacts. Those are all of our model's assets. That could be the model itself, that could be the weights of the model, that could be any additional data structures that our model needs, like dictionary encoded values. Then we have our deployment considerations. How often are we going to retrain? What are our compute requirements? Do we have any sidecars? Are there any audit tables that we need to build? Model artifacts and deployment considerations together comprise model ops. Model ops practices ensure that the trained model artifacts are persisted, updated, and available for other services and available for observability. Let's dive into the specific types of model artifacts we need to manage. First, we have training checkpoints. Training checkpoints are progressively serialized training results. These can be persisted to disk or persisted in some remote cloud storage. Training checkpoints are great if your model needs to train for a couple of days. That way, if there's an interruption, you don't have to start all the way over. Next, we have the trained model itself. Again, we can serialize that model and save it to disk, or we can persist the model in a location that's readable by your inference service, like remote cloud storage. We also need to manage the trained model's hyperparameters. Those we can record to an audit table, for example. We also want to make sure that we're cataloging our training data. We can do this in several ways. We can create hashes of our training data and persist those hashes alongside our model. Or if our data is somehow sequential, we can persist the indices of the first and last point that we used for training. Next, we want to record our evaluation metrics to an audit table to make sure that as we retrain, we're getting consistent results from training period to training period. Finally, we also want to make sure that we record our feature importances. Those need to be recorded in our audit table as well. This is going to help you understand if a particular feature is overly weighted or underweighted, or if it's being attacked or exploited by attackers, or if the feature is no longer useful. Now let's examine the deployment considerations in detail. Again, our deployment considerations include retraining and compute requirements, as well as sidecars and other requirements. Some key questions to answer to iron out your deployment requirements include, what automated pipelines are we going to use for our model deployment? How often is our model going to be retrained? What are the compute requirements for retraining? Are we doing incremental training? Are we doing fine-tuning? What are we going to do about data persistence? Again, those encoded dictionaries or data enrichment or any caching that we want to do. Will the training service need to have other persistence requirements? And we also need to consider temporary data stores between model training runs. Let's recap some of the key MLOps considerations with regards to model deployment. We should consider the availability of our data structures and model artifacts that are created during training. We need to focus on persisting a record of our training data securely. For reading and writing our trained model, can we write to disk? Is that a safe action to take? When we're reading in our trained model, are we using a pickle file? We need to consider hardware requirements for training. If sidecars are required, are they allowed in our cluster if we're training on Kubernetes? Container resource constraints might need to be disabled. Finally, there's going to be so many audit tables. An audit table for your model version, for your model evaluation results, for feature importances, for your data cataloging, and then also for signing your model. Serving and inferencing. There's going to be different considerations if you're doing streaming, batch, or one-off inference. Let's start with streaming inference and its specific requirements. With streaming data, preprocessing needs to be minimal or extremely lightweight. Streaming data requires online or real-time inferencing. If you're trying to classify new observations at rapid speed, you want to have as minimal data processing as possible. We might need to use something like Kafka in our architecture that can handle those streaming data streams. Latency needs to be considered for streaming data. Bandwidth is also very high, and you need to make sure that your latency is extremely low as it can get, because you're doing real-time, lightning-quick inference. Given the generally high bandwidth in streaming data services, your inferencing endpoint might need to be horizontally scaled to handle the load. So it's important to consider if the inference system is going to require any kind of elasticity. Data retrieval needs to be minimal or none. We need to make sure that everything that model needs to make a decision is already available for it. So it's not going back and querying other services as it's trying to classify each individual data point that's streaming into our inference endpoint. Finally, costs are mostly going to be incurred from the calling service. Next, we have batch inferencing, which has quite different characteristics from streaming inference. In batch inferencing, we have a higher degree of flexibility for our data preprocessing. That's because batch inferencing runs on a schedule and performs the inferencing task in bulk on new data. For example, a batch inferencing service may run once an hour. It'll look back at the data points from the last hour and make some determination about those data points. Given the fact that batch inferencing will run either on a schedule or per some other predefined trigger, the only constraint on data preprocessing is that it needs to complete before the next batch run. With batch inferencing, your architecture can be quite flexible. The main requirement is to fit the needs of the periodic run. Your bandwidth can be high because you may be pulling a large amount of data from a remote data store, but bandwidth really depends on the amount of data associated with each batch. Latency is less of a concern here because, again, this is running at some predetermined time and it might not be a blocker for any other system. Your batch inferencing might need to elastically scale depending on if your batch sizes are dramatically different between individual runs. Another use case for elastic scaling would be very infrequent batch runs. Maybe you only need to run batch inferencing once per week. In that case, it may be a good idea to use serverless inferencing to avoid having resources sit idle. Your costs are going to be a lot more predictable than with streaming or online inferencing because we generally have a good idea of how much data will be used at inference time. With one-off inference, meaning a one-time run of your trained model, the requirements are even more flexible. In that case, you might not even need to persist your pre-processing algorithms from your model training stage because you might run model training and inference as part of the same service on the same resource. Your architecture will only depend on what best suits your model inference needs. That could look like training and inferencing on the same machine. There's a good chance that latency is not going to impact the effectiveness of your one-off inferencing architecture. Scalability, data retrieval, and costs are going to depend on the size of the model and the size of the data that it's inferencing on. Let's review these key considerations for our different kinds of inference. Streaming and batch and one-off inference are all going to have different architectural requirements, different compute requirements, and different costs. Your inference service needs to be able to use the same data processing techniques that the model training service. Without repeating your pre-processing on new data at inference time, your model is not going to be able to work with the incoming data. Your endpoint availability is going to be a top concern during inference. There are many negative consequences of having an inferencing endpoint that is not highly available. Either customers who are using your AI or ML service are not going to be able to actually get a result, or if you're doing some internal AI or ML, your business stakeholders are not going to be able to get a result. We need to think carefully about bandwidth and latency when we're creating this inference service. Our costs can be unpredictable, especially with streaming or online data. We need to make sure that our model decisions can be recorded to an audit table. Every data point that receives some kind of operation from our model should have its results stored somewhere. Next up is monitoring and maintenance. This is our observability stage. For performing maintenance, we need to make sure that we're regularly revisiting our metrics that we used in evaluation to determine if our model performance has degraded. If our initial training metrics were accuracy, precision, recall, and F1, and our metrics looked great when we were training, it's important to be able to tell if accuracy, precision, recall, and F1 continue to look good as our model continues to operate. If those metrics gradually decline over the course of weeks or months, we need to make sure that we can detect that decline and correct our model drift. Data quality is also a big consideration. We need to make sure that we can identify any failure modes within our data pipelines between both training and production. We also need to make sure that we're monitoring for any kind of cardinality shifts in our data, any missing data or data type mismatches, and out-of-range values. Being able to detect data quality issues before the data gets to the stage of being used in a model, whether for training or inference, is important. Otherwise, we are introducing failure modes in our model. Having observability baked into our data pipelines is a proactive approach to preventing downstream issues. Then we have explainability. Explainability refers to the techniques and metrics that can be used to understand our model and our model's decisions. Metrics like feature importances across training and validation runs helps us to introspect on our model and build confidence in our model's decisions. They also help us continuously improve our model. When it comes to monitoring drift, we want to make sure that we're monitoring for a change in distributions over time. We can measure our model inputs and outputs and the actuals of the decisions of a model. That is going to help us understand if our model has grown stale or if there's any data quality issues or any kind of adversarial inputs to our model as well. Let's look one more time at the rules behind the AI/ML lifecycle. We talked this through a little bit earlier. In the AI/ML lifecycle, domain experts, data engineers, data scientists, software engineers, site reliability engineers, and observability teams all work together to build, test, deploy, and serve a model. These are the bits that data scientists are trained to do. In your data science coursework, these steps will likely be the most familiar. We become experts at data collection and pre-processing, experimentation and evaluation, and monitoring and maintenance. And this is what data scientists are actually doing. Depending on the organization that you work for, you may be responsible for end-to-end implementation of your work. This is one of the big reasons that I wanted to have MLOps and the group project structured the way it is, because you're going to be able to get a sense of what's required to actually implement a model in production. If you're at a large organization that's well-resourced, or if you're working at an AI/ML-focused organization, you'll likely have distinct engineers working on each part of this. But if you're building AI and ML models in a smaller team for a particular business function, you might be the one responsible for 100% of this work. Just getting used to what we're dealing with when we're implementing models in production is going to be very useful. If you're working in product or project management in the future, this will help you understand all the stakeholders that you need to work with in order to implement a successful AI and ML product. All right, thank you so much. That's the lecture for today, and we'll see you next time for a continuation of our MLOps unit.